Welcome everyone. So let us review what we learned so far. We start talking about a differential equation. Review. A differential equation is an equation with the derivatives or containing the derivatives of y if y is written as a function of x. It means that your x is a free variable and y depends on x. We talked about the order of a differential equation. The order of a differential equation is the highest order of the derivative in the equation. Then we said that, hey, if we have an nth order differential equation, we can represent it this way. When y is equal to f of x, an nth order differential equation is denoted by, we have a standard form, which is, for example, f representing a relation, a connection between x, y, and the derivatives. And remember that we stop at the nth derivative of y. And since it's an equation, we set it equal to 0. Well, we talked about a linear differential equation as well. We said that a linear nth order differential equation is denoted by, here we have some coefficients of the derivatives of y. And suppose here the order is n. It means that the highest derivative appears in your equation is n. So you're going to see a sub nx, the nth derivative of y, plus coefficient of the derivatives. Those are all either constant or terms or functions of independent variable x. A sub n minus 1x, the nth minus 1 derivative of y plus the middle terms. We have some middle terms. And then here you have a sub 1x, the derivative of y plus a sub 0x, y equals to, well, you're going to get a function or a constant related to x itself. We call it a linear nth order differential equation. Now remember that here you say that y is equal to f of x. So last time we discussed this case that if we change the independent variable, if y is equal to, for example, f of t, all of these coefficients are going to be in t. So note that if y is equal to f of t, then it's represented as a n t, the nth derivative of y, plus a n minus 1 t, y, n minus 1 derivative of y, plus the middle terms, a sub 1 t, the first derivative, a sub 0 t, y equals to g of t. And again, note that we said that if x is a function of y, then we have to switch everything. So another note. These are important. If we change the function, we have to be careful about the definition that you're representing for that linear or other type of differential equations. If you have x equals to, for example, h of y, then the coefficients must be in y. So you can write it this way. An y and derivative of x plus an minus 1 y, the n minus 1 derivative of x, plus the middle terms, a1 y, the first derivative of x. Remember that for the first derivative, you can put a dot on top of x as well, then a sub 0 y, x equals to, for example, let's just have some function like k of y. So depending on how you define the function, you have to change the definition for linearity. After these introductions, we talked about the solutions of differential equation. Okay, solutions. We are just reviewing the materials that we learned last week. For the solutions, of a differential equation, we have the following cases. The very first case, sometimes we have explicit solution for a differential equation. So the first one is explicit solution. Well, it's given to us as, for example, for function, if you have y equals to f of x, or when you have a differential equation and y depends on x, well, we say that phi of x is a solution for the differential equation if it satisfies the differential equation. Explicitly defined, and when we plug that into the differential equation, we see that hey, left-hand side and right-hand side are equal to each other. Left-hand side of the equation is equal to the right-hand side of the equation. Sometimes we're not that lucky. We have a combination of x and y's. We have the solution written in implicit form. So to implicit solution. So sometimes you get a relation g of x and y equal to 0 as a relation between x and y, like x squared plus y squared equals to 25 is a solution, implicit solution for the differential equation if we can find at least one explicit solution and the implicit, and from the implicit differentiation, of g of x and y equal to 0, it satisfies the differential equation. These are the things that we talked about last time. Well, I expect you to ask, as a mathematician, can I solve any differential equation? Can I find explicit solution or implicit solution? Is it possible? Question. Can we find explicit or implicit solution for a differential equation all the time? Well, can you solve any differential equation? Is it possible? Unfortunately, the answer is no. Sometimes we are not able to solve a differential equation. So I expect you to ask, well, how do I analyze the solution then? How do I know about the solution? What is the behavior of the solution? What is the nature of the solution? So the answer is no. There are differential equations that there is no explicit or implicit solutions for them. And you can say that yet maybe you can find a solution for those differential equations. That's why we are learning math. So I expect you to ask, how do I analyze the solutions then? Then how do we analyze the nature of the solutions? Well, we can use the concepts that we learned in calculus. Calculus is a tool, is a technique that helps us to analyze solutions in a differential equation class. One of them is slope fields. Slope field. And also something new, not that much new. It has to do with the level curves, but in this case, we are dealing with the derivatives, but the level curves of the derivatives, and we call it isoclines. Both from calculus. So this is one of the apps that you're going to use to analyze the behavior of your differential equation and its solutions. Let's go to the board and write down the definitions and some examples. So from implicit, explicit solution to implicit, explicit solution to implicit solution, and now visualize them. Visualize the solutions. So, well, the very first one is using slope field or the direction field. Example. Let me explain this through an example. Question says, graph the solution of the differential equation. Here you have dy dx, the first derivative of y with respect to x is equal to x squared minus y. Okay, very good. So we have a differential equation. We are interested in analyzing the solutions. What is the nature of the solution? What is the behavior of those solutions for this differential equation? To visualize the solutions of the differential equation, we can use the slope field or the direction field. Slope fields. Well, how do we graph the slope fields? Remember that in calculus, we learned that if we have time, we can form a table. We need a table with x values, with y values, and with the derivative, which in this case is given to us as x squared minus y. Very well. If you have time, I encourage you to just plug in as many points as you can and see what is the behavior of the solution sets for the differential equation that we have. Okay, so x, y, these are just random numbers. We plug in different values for x and y. We calculate y prime and start using those small little arrows to visualize the behavior. And plug some values for x and y. Very good. So let us start by plugging, for example, 0. Let x be equal to 0, y be 0. So it says at the origin, what is the rate of change? The rate of change is 0 squared minus 0 or just 0. So you say that, hey, at the origin, 0 and 0, the slope or the rate of change is 0. What's the meaning of that? It means that if you want to use a very small arrow representing y prime equal to 0, it's going to be just a flat arrow. There is no change. It's not increasing, it's not decreasing, it is just 0. So let's take a look at this. Here in xy plane, x-axis, y-axis, at 0 and 0, at the origin, you're going to have a very small flat arrow. This arrow has slope equal to 0. At the origin, the slope or rate of change is 0. This small arrow here. You continue plugging different values. Suppose your x is 1 and your y is 0. X is 1, y is 0. So let's calculate the rate of change. It is 1 squared minus 0 or just 1. What does it tell us? It tells us at 1 and 0, the slope is positive 1. At 1 and 0, the slope is 1. Where is 1 and 0? Suppose 1 and 0 is just right here. The slope, it means that we have to graph a very small piece of line or an arrow representing the rate of change. Rate of change is 1. Here we go. This is 1 and 0. We can continue this process. We can plug in different values. We can plug in, for example, 0 for x and 1 for y. The rate of change is 0, minus 1, or negative 1. So at 0 and 1, the slope is negative 1. We can continue this. We can plug in 1 and 1. Y prime is equal to 1 minus 1 or 0. Continue this process if you have time. Well, luckily for us, we're going to use technology to visualize the behavior of the solutions for this differential equation. So let's take a look at our technology here. Okay, so we have x squared minus y. Very well. See, these line segments, they all changed. It means that you have the slope field or the direction field of this differential equation, y prime is equal to x squared minus y. So I'm going to click on some of these arrows here. See if it can give me something meaningful. Let me click on this. Oh, wow, I got a parabola. Here, I got another curve. Let us take a look at this one. Another parabola. Wow, it's just changing the behavior. So you see, you have the behavior of these solution sets using this app. Even though you don't have the implicit or explicit solutions for this differential equation, but you know how it behaves. There you go. So this is the method of direction fields. Let's see. Let us go over another example for you. Question says, well, graph the solutions of the differential equation, which is given here to us. Here we have dy over dx, which is given to us as, well, 0.2 x times y.
Professor, remember to show the board.
Very good. So graph the solutions of dy over dx equals to 0.2 times x, y. Very good. So we can come up with our table, x, y, dy dx or y prime equals to 0.2 xy. Plug in different values, complete the table. Again, if you have time, I encourage you to do that. And eventually, you're going to use technology. So let us take a look at our website here, 0.2 x times y. Very good. So this is the behavior of the solution sets for this differential equation. You can click on different direction fields, slope fields, and as you can see, these are the behaviors, the nature of the solutions for this differential equation. It's divided up into two pieces. The first piece, all concave up, and the second piece, all concave down. Very well. So other than the slope fields, direction fields, they have something else to visualize the differential equation solutions in the case that, well, we cannot find explicit solution, implicit solution, or in the case that you're interested in general visualizing the solutions. That method actually is helpful when you want to deal with slope fields or the direction fields. Again, these two methods are old-fashioned methods. Nowadays, we just focus on technology, but it's worth mentioning that we have different methods in analyzing the solutions of differential equations. One of them was slope fields, and the other one is called isoclines. So, isoclines. Let me explain this through one example for you. So this is page 3. And here we have this example. This example says, hey, graph the solutions of the differential equation, which is given to us as y prime equals to x plus y. Very well. So in this method, using isoclines, we're going to visualize how to graph the level curves for the derivative. In the method of isoclines, we use the level curves for the derivative, or let's just write down dy over dx. So remember the level curves. To find the level curves for a function, we take that function, set it equals to some constants, and graph those. So as a review, this is from calculus. Set it equal to some constants and graph it. Then we get the level curves of that function, but in this case, we get the level curves of the derivative or the isoclines. So let the derivative be equals to constants 0, 1, -1. Let y prime be equals to 1. Let y prime equals to -1. You can continue this process. So again, you are setting your derivative equals to constants. In previous method, using the slope fields or direction fields, we had some values for x and y, and then we evaluate y prime. Here, in the opposite, we take the derivative and we set it equals to some constants. Okay. Y prime is equal to 0. But what's the definition of y prime? It is x plus y. Okay. It says, hey, slope, rate of change is equal to 0. So it is rate of change is equal to 0. X plus y is equal to 0. So y is equal to -x. What's the graph like? X-axis, y-axis, y equals to -x. Here you have a decreasing line. So this is your line that you have here. On this line, slopes or rate of change are 0. Okay, here we go. On this line, all slopes are 0. It means that I'm dealing with flat lines. On y equals to -x, we have slope equal to 0. Okay. Y prime is equal to 1. The slope is 1. Rate of change is 1. But what's the definition of the derivative? The definition of derivative is x plus y. So x plus y is 1. Y is 1 minus x. What is this line? This line is just right here. On this line, all the slopes are positive. The rate of change are positive. So you have this behavior. 1. You get some lines and they have positive slope. Slope is 1. What about -1? I set the derivative equal to some constants. In this case, it is -1. Rate of change is -1. It means that your slope is -1. What's the definition of the derivative? It is just x plus y equals to -1. So y is -x minus 1. So now you can see these lines have some lines with negative slopes. Slope is -1. Very good. Okay, let's see. Here we have -1, so it is along with the line itself. Again, if you have time, set the derivative equals to some other constants and solve for the derivatives and see the behavior. We can use technology to double check the work. Here we have y prime equals to x plus y. There you go. This is the slope field, the direction field. In the method of isoclines, it helps us to visualize the direction field or slope field a little bit easier, a little bit faster. But as you can see, the fastest way to analyze these solutions, the behavior of these solutions, is to use technology. So repeatedly in a differential equation course, you might see initial value problems. So recall that at the beginning of the class, I talked about the case that you have a friend in biology and your friend asked you to model the following situation. The time, this is the biology case. The time rate of change of the population is proportional to the population. Well, your friend asked you to model this, and remember that we say that suppose the population is P of T, this is your population. I don't know what that population is, but I need something to model this mathematically. The rate of change of population with respect to time is equal to K, which is a constant, times P of T, which is the population. Now, suppose your friend says, well, at the start of the case study, when we checked that, for example, population, there were 100 frogs, 100 fish, or 100 organisms in that population. So your friend poses this condition. P of 0 is 100. This is a condition that we are imposing to this differential equation. We say that, hey, after solving this differential equation, the solution must satisfy this condition. This is called initial condition. This is called the initial condition. And the whole thing is called the initial value problem. And this differential equation, along with its initial condition, is called an initial value problem. It means that you are imposing an initial condition here. For example, at time 0 or at the beginning of the study, the population or the y value for your function was some numbers, in this case, 100. Example. Show that phi of x, which is given to us as sine x minus cosine x, is the solution for initial value problem IVP, the second derivative of y plus y is equal to 0, and you have these conditions. When your x is equal to 0, your y is -1, and when your x is equal to 0, your derivative is equal to 1. Okay. So we want to show that this function satisfies the differential equation, the initial conditions given to us here. Our goal is to show that this is our goal. Phi of x, which is defined as sine x minus cosine x, satisfies the differential equation and the conditions. Very well. So let us begin. For the differential equation itself, for the differential equation, you have the left-hand side, right-hand side. On the left-hand side, what do we have? The second derivative of y plus y, and on the right-hand side, you have 0. Left-hand side, right-hand side. Very well. Okay. What's the derivative of phi of x? What's the second derivative of phi of x? The first derivative, let me write it here for you. The first derivative is just cosine x plus sine x, and its second derivative is equal to negative sine x plus cosine x. So replace that on the left-hand side. You get negative sine x plus cosine x plus y. Y is sine x minus cosine x. Well, these are all opposite of each other. On the left-hand side, we have 0. On the right-hand side, we also have 0. So phi of x, which is sine x minus cosine x, satisfies the differential equation. How about the initial conditions? For y0 equals to -1, it's not that hard. It says if you plug in 0 into phi, the output must be -1. Again, left-hand side, right-hand side. Okay, the left-hand side. So here you have phi at 0, which is sine 0 minus cosine 0. This is 0 minus 1, which is -1. -1 and -1 are equal to each other. So it satisfies the first condition. The first condition is met. Now we have to move to the second condition for the derivative at 0 equals to 1, left-hand side, right-hand side. Okay, left-hand side, wherever you see the derivative, plug in 0. You get cosine of 0 plus sine of 0. This is 1 plus 0, which is 1, equals to 1. What's the meaning of that? It means that phi of x as the given solution satisfies all conditions. Also satisfies the conditions. This is an example of the initial value problem.